Hello, good evening. Carrie and Jason here. We are going to talk about combining forces. In 1494, Luca, a 615-page condemned, Luca wrote this book for merchandisers by hidden note, which made mathematical scientists think about permutations and combinations in various situations. The similarities and differences is combinators, the order doesn't matter. But in a permutation, the order matters. The similarities between the two is it is talking about grouping different items or numbers together. And in real life uses, with combinations, you have pizza toppings, putting on your shoes, and interior design. And what I mean by that, do you really have to put, the left shoe on right first or the right shoe? It doesn't matter. And the same thing when you're ordering a pizza, especially online, because it doesn't matter if you choose cheese first or you do the meat first, come back to cheese, you'll have a pizza by the end of it. And then you go to the permutations. This is like work schedules. If you think about nurses in hospitals, they have to have a specific schedule for their ladies, or else some people are going to be working triple shifts, or others are going to be having no hours.
All right. All right. Well, thank you, Carrie. Appreciate that. And my name is Jason. I'm going to take the rest of this presentation over. So we're going to go through the mathematical walkthrough of the amount of permutations and combinations once you're going through n amount of objects. And n is the variable for the choice that you have out of the total number of objects you're given to choose from. So with combinatorics, we're given a problem where in this instance, we're approaching a hot dog stand. And at the hot dog stand, there's 5 possible condiments to choose from, but we're only able to choose 3 condiments due to lack of money. So how many overall combinations of condiments for the hot dog do we have? So as for here, we have our equation for combinatorics. So we have 5 right here for our first variable, which is the 5 possible amount of condiments, and then 3 is the 3 total that we choose. So with this, we put those into our combinatorial equation. So we're starting out with the total possible number of condiments on top, for that is 5 factorial. And under we have the total number we can choose from, which is 3 factorial minus, and then that's multiplied by 5 minus 3 to give us a 2 factorial. So then what we do with that, we break it down into, we break down the factorials, and we have 5 times 4 times 3 times 2. We take both of them all the way down to 1, and then we cancel out any similarities. So we get rid of the 3's and the 2's. And by that, then we just have 5 times 4 times 1 gives us 20 for the first. And we have 2 times 1 times another 1, which is still basically just 2 times 1. So then that's 20 over 2, which equals out to 10. So we have 10 possible overall combinations for all the condiments we can choose for our hot dog. Wonderful example, yeah. Now for our permutations, in this instance, we have combination lock that holds 1 to 6 digits, but we only need 2 to actually gain entry into the lock. Since we know that order is required with permutations, like Carrie said, then what is the maximum amount of combinations for our 2-digit lock? So if you look over at our permutations formula over here, we have 6 as the total number of numerals we can choose from, but 2 are the only ones that are actually required to gain entry into it. So with that said, put our total number of numerical options into the top part of our fractional equation, and that is 6 factorial. And what we do with that, we subtract the total number from the amount that we actually only need, which gives that to a 4 factorial. So that's 6 factorial over 4 factorial. We break that down to the nearest number in common between the two, which is 4. And with that, since they are the same, then we cancel them out. So we get rid of the 4 and the 4 on bottom, leaving us with 6 times 5, which equals to 30, which means there's 30 maximum amount of combinations for a 2-digit lock. And there's our works cited, and this has been Carrie and Jason. We appreciate you joining us today. Thank you.